So thank you very much. So first of all, thanks to the organizers for this great workshop. Yes, I've heard a few, some very nice talks concerning topics that I'm really interested in, like back reaction or semi-classical gravity. So these are the two big points also of my talk. So I'm going to talk about holographic stability of maximally symmetric spacetimes. So I'm a second-year PhD student at Université Paris Cité in the laboratory APC for astroparticle and cosmology. So first of all, I'm just going to present this topic by three statements. So the standard model of cosmology relies on the theories of fundamental interactions, including GR and QFTs for general relativity and quantum field theories. However, one of the less understood aspects of cosmology is the interaction between the geometry of spacetime with quantum field theories, especially in a non-perturbative regime. When quantum fluctuations of the matter content act on the background geometry, we say that the matter fields backreacts, which could lead to an instability of the background geometry. So the outline is 3 points also. The context first of semi-classical gravity. Then I'm going to present how to derive the 2-point correlation functions of the stress tensor and the metric perturbations. And then I will discuss the interpretations of their poles of these 2-point functions and conclude on the stability of these maximally symmetric spacetimes. First, the context of semi-classical gravity. So I'm not doing only semi-classical gravity, but I'm also using holography. So just to present a little bit, the problem is that usually people will do a perturbative quantum field theories and couple it with gravity, and that coupling can lead to an instability. But the question is instability an artifact of perturbation theory? So a way to bypass this perturbative approach is to use the holographic principle, which is a conjecture, and it suggests that the strongly coupled regime of a quantum field theory is equivalent to a higher dimensional theory of gravity. So here, just to sketch this holographic principle, I used ADS5, which we call the bulk spacetime, and the boundary is the universe we observe. So for instance, in particular, if there is pure gravity on this anti-de Sitter 5-dimensional spacetime, then when we will observe at the boundary, at the conformal boundary of this spacetime, it is a boundary term. And it's in particular, you can obtain the stress tensor, and the stress tensor will have the same trace anomaly as n equals 4 superior-Mills theory in the large n limits, because we know how to compute it in the large n limits. So we show that these two trace anomalies coincide if the parameters are related like this. So L is the characteristic scale of ADS5, G5 is the 5-dimensional Newton's constant, and N is the Color number of this CFT, this conformal field theory. And we can, using this holographic setup, we can have new insights on, for example, a Starobinsky model. So this is the project I'm working on. It's just to present this historical model. It consists in 3 massless conformally invariant field theory in 4-dimensional FLRW spacetime. And this model will have such a trace anomaly, the same as I told you in the previous slide, and it just consists in 2 parameters of the theory, so M and H0, and the trace of the stress tensor will be this. And starting with this matter content, one can compute the evolution of a small isotropic perturbation, delta, which is just a shift of the Hubble rate. So it preserves FLRW. But if we start from de Sitter, we can see that by showing that the solution for this delta over time, it will stay in de Sitter or not. And this statement if it stays in de Sitter or goes somewhere in FLRW depends only on the sign of m squared, which is basically the mass of the inflaton. So this is from the 80s, and we extend this idea to a strongly coupled CFT, so using holography, and also we study arbitrary metric perturbation, which don't preserve necessarily FLRW. So now we have the setup, and we can compute the two-point correlation functions. So these are just details about the holographic setup, but first we need to obtain the one-point function of the stress tensor. And so the metric of the bulk spacetime is of Pfefferman-Graham form. This is this metric. And the slice metric, this little g, has a near boundary expansion. So in small values of rho, which is the holographic coordinates, this scale goes to 0 at the boundary. But when we are near, the leading term is basically the geometry of the spacetime we are interested in. And then if we fix the geometry of the boundary to be de Sitter, for example, all the terms of the near boundary expansion will be known because it's just a cinch. But if G0 is arbitrary, because we will include perturbations, then the one-point function of the stress tensor, the renormalized stress tensor, will be a function of G0 and G4. And for an arbitrary geometry, only the trace of G4 is known in terms of G0. So now we include metric perturbations around de Sitter or any maximally symmetric background. And these perturbations are delta of G0. And they are arbitrary, but we can still fix the gauge in order to decompose our perturbations into 1 scalar and 5 tensor degrees of freedom. So tensor because they are transverse and traceless, and psi, the scalar mode. So now we can compute the two-point functions of these two different metric perturbations, the scalar and the tensor. So just the definition of the two-point function, and this is the action of our theory. There is the CFT part and the gravity part, which includes Einstein-Hilbert, and also quadratic curvature terms, because these are the terms that are finite in the regularization procedure, the holographic regularization procedure. So above, it will be vanishing, and below, it needs to be renormalized. So then we can compute the scalar and tensor perturbations. They are decoupled to each other. So we have only two different two-point functions, the tensor and the scalar. And we get this delta G4 from the bulk dynamics, because as I told you, it was unconstrained. But if we compute the dynamics of bulk metric perturbation, then we obtain the variation of G4 and we can compute the two-point functions. And the price to pay is that to do a separation of variables, we decompose the metric perturbations into eigenvalues of the slice Laplacian, so the de Sitter Laplacian, using this eigenvalue nu squared, which encompass the stability or instability behavior. So just to tell which is a stable or an unstable mode, we just take this nu, or in Minkowski spacetime, we take k square, which can be related to nu in the flat space limits. So what is an instability? A spacetime is unstable if and only if the retarded green function of the metric perturbation diverges with time. So using the fact that we have decomposed our metric perturbations into eigentensors of the Laplacian, it's equivalent to say that Minkowski spacetime, for instance, is unstable if the mode k in the complex plane is such that the real part of k is different from 0. So it will mean that the retarded green function will be diverging with time. And you can see that because there will be a complex frequency. So like the imaginary part of a frequency will make the wave blow up with time. And the same with de Sitter and anti-de Sitter. Using this eigenvalue nu, the criterion using the definition of nu is such that the real part of nu in absolute value is bigger than 3/2. And when it's really equal to 3/2, it's just the massless graviton. And in ADS, it's a bit different. It's unstable when the real part of nu is 0. And this comes from the BF bound analysis, because in ADS, it's a bit different. Negative mass squared are allowed, but below a certain bound, it will really be unstable because there will be a normalizable solution which diverges with time. So using this criterion, then we can look at the zeros of the inverse two-point function or the poles of the two-point function for the tensor mode here for flat space. So the boundary is a Minkowski space, and I look at the zeros of the inverse two-point function, so the classical solutions of my theory. So here I just represent the complex plane for K, the real part of K and the imaginary part of K. And the orange lines are the zeros of the imaginary parts of the inverse two-point function, and the blue lines are the zeros of the real parts. So the true poles of my propagator are intersections of the lines, which I denote with colored dots. And beta here is the parameter of my action, one of the two curvature squared term, and alpha is another one, but the flat space tensor instability does not depend on alpha. So I just vary beta here. So when I vary beta, you will see that two unstable poles will merge on the real axis, and then they move off the complex plane. It's still an instability. And then when beta is increased up to infinity, it will go to the origin. So the conclusion of this is that flat space is always unstable because there is always a real part for K. And it's only stable in the asymptotic limit when beta is infinite. So we can do the same for curved spaces with the different stability criteria. And then we can, so what we did is just a summary of all of these in parameter space. So checking for which value of beta the theory becomes stable. So in vertical axis, it's beta. And when there is a dot here, it's that the theory goes from unstable to stable. And the color is for different values of alpha. And in vertical axis, it's the curvature of the theta. So here it's just a summary of some numerical results concerning the location of poles of the two-point function for the tensor two-point function. And the same in ADS with this different plot, because also the stability criterion was different. But still, there is a similar behavior where for a given value of the curvature, the stability, the transition from instability to stability will look a bit different on the right-hand side of this panel. The last quantity I can tell you about is the characteristic rate of the instability in the theta. So if there is an eigen scalar or eigentensor of the theta, for large time, they will scale as an exponential of omega t. And this omega is just proportional to the Hubble rate and the difference between the real part of nu and 3/2. So when, as I told you, when a given pole in nu space is unstable, it's when the real part is above 3/2. So we can compute this omega and compare the instability of the scalar mode with the instability of the tensor mode. And these panels, they just compare the scalar versus the tensor instability, and especially they compare the values of omega. So in green region, in the space of alpha and the curvature, the green means that the tensor instability dominates. In white, it's when the scalar instability dominates. And in blue, it's when both are stable. So there is no instability. Both tensor and scalar are fine. So and in the red line, I just plotted the value of the curvature, which compares to the papers from the 80s, so by Valentin and Starobinsky, when they fixed the relation between the curvature and the cosmological constant to this value. So gn square h square equals 4 pi. So just to say that when I vary beta, the tensor instability is less and less important. As we have seen, when we increase beta, the tensor instability, when beta goes to infinity, it will disappear. And also, a conclusion to this is that the tensor instability is important too. We should not focus only on the scalar inflaton, but when there is a strongly coupled CFT with holography, for example, the tensor mode is also very important. So as a conclusion, we have extended the holographic two-point functions for the stress tensor and the metric perturbations because they are the same in the maximally symmetric spacetime with any curvature. And we have found some numerical and analytical methods to determine stability. I didn't talk a lot about the analytical methods, but I just compare some approximations with the numerical results too. And the tensor instability can dominate the scalar mode. And the scalar mode is usually studied in inflationary models. So it will be interesting in the future to look more to these tensor instabilities. And as an outlook, we can study the back reaction with a QFT and not a strongly coupled CFT. So the difference in the holographic procedure is just that we can include a running scalar field in the bulk, which back reacts also in the bulk geometry. Here we, as far was what we did was just take a bulk ADS5 just with perturbations. But if we include a running scalar, then we will be able to study QFT. And then we can also generalize our results to FLRW background geometry, which will be even more interesting for cosmology. And it will be a bit more complicated because we don't have, with FLRW, we lose the maximally symmetric aspects. So thank you very much. And that's it from me.
Okay, thank you. It was a very interesting talk. So now it's time for questions. So in the audience, do you have any question or comment? Okay, if not, I can start. Yeah, when you were talking, I was during all your talk thinking, how can you generalize your results with other background metrics which has less symmetries, no? And then you said that this is a future perspective. So can you comment on a bit on this? How can you extend your analysis when the spacetime is not maximally symmetric?
So as far as I'm concerned, so far I don't know exactly how to generalize to any spacetime, but there is like a more trivial generalization, and FLRW is part of this because FLRW is conformally flat. So what we can do with ADS-CFT, what I know about ADS-CFT is that the bulk metric is ADS5 for now, but it will work for any asymptotically ADS spacetime. So when rho goes to 0, this coordinate system tells you that the bulk is asymptotically ADS, and you can slice it with, so this little g is the slice metric. And so, for example, ADS can be sliced with FLRW because it's a conformally flat spacetime. So the two-point functions will look different, but the setup is very similar.
Okay.
A different slicing of the bulk metric.
Okay, thank you. Okay, so maybe we have another question from Gerardo. Gerardo?
Yes, hi, thank you for this interesting talk. I'm not sure I've exactly understood when does holography enter in the picture. I mean, because the analysis seems to be a perturbative gravity around a given background. So can you comment?
So gravity is classical. I treated it as a classical field theory. But holography enters in the one-point function and two-point function of the stress tensor. So basically, when I write the action, it's like a modified gravity action here. But the parts of the CFT here comes from holography. And the conjecture is that the stress tensor you obtain from this term of the action that comes from a bulk ADS. So it's really like a boundary term of classical gravity in a 5-dimensional spacetime. And what you obtain on the boundary will be the one-point function of a strongly coupled CFT stress tensor. So it's really the matter content which differs.
Okay. So you are okay. So you are using that to solve the background and then study perturbations on top of that background.
Yes, yes.
Okay. So this part I miss it. You probably.
Yeah, sorry, maybe I was not very clear on this part.
Yeah. I understand now. Thank you very much.
Okay, we have time for the last question. In the chat, we have a question from Sebastian Schuster. Did I understand correctly that in this ADS CFT context, Minkowski is not stable, the animation you showed? How does this connect to the nonlinear stability results of, I don't know if I know how to pronounce it, Christodoulou and Kleinerman, or similar?
Yeah, the first part of the question is true. With ADS CFT, we find that flat space is always unstable, even if the characteristic rate of the instability can be very small or very large, depending on the parameters. And that's really due to the coupling with the CFT. So I don't know exactly about the setup of this nonlinear stability results, but maybe they just include modified gravity, or I don't know exactly. So yeah, basically when I decouple the CFT, flat space is stable. So it's decoupling the CFT can be done. It's equivalent. I can take beta to infinity, and then it will dominate the CFT part of the action. And you see that when beta goes to infinity, it goes to a stable region. Basically, it goes to the origin where you have only the massless graviton at k equals 0. And you can also decouple the CFT by setting n, the Color number, to 0, because the stress tensor is proportional to n squared. So, and this limits, yes, flat space is stable.